Okay, now let's look at some of the homework in 15.6. I'm going to start this with number 6. We have f of xy. I want to find the directional derivative of f at the given point and the angle. So first, to find f of x, we have to use the product rule. Derivative of xy with respect to x is y. And f of y, we don't need the product rule. We have to take the derivative of sine, which is cosine. With respect to y is x. Okay, u is the unit vector in the direction of pi over 3. Pi over 3 is 60 degrees. So opposite 60 is square root of 3 over 2. That's the sine of pi over 3. And the cosine of pi over 3 is a half. So those are the components. So u is going to be 1/2 square root of 3 over 2. Okay, so du of f is this. And at the point 2, 0, f of x is sine of 0, which is 0, plus anything times 0 is 0, so this is going to be 0. And f of y at 2, 0 is 4 times the cosine of 0, which is 1. So that's going to be 0 plus 2 square root of 3. Okay, 8. I want to find the gradient of this function at the point 1, negative 3, and the u is negative 4/5, 3/5. So f of x, y is a constant, derivative of ln x is 1 over x, and f of y is just going to be ln x. So evaluated at 1, negative 3, this is going to be negative 3 over 1, and this is going to be ln of 1, which is 0. So we have negative 3, 0 dotted with u, which is going to be 12/5. That's it. Oh, we want the directional derivative, and that's going to be the gradient Oh, that's what I found. Oh, okay. The gradient, I did part C ahead of time. Let me go through the steps. A, find the gradient. Okay, so the gradient is fx, fy, which is negative 3, 0 at the point. Oh, that's part B. A is yx, ln x. Sorry about that. Then I plug the point in and get part B, and this is part C. This is the directional derivative at P0 at the point. Okay, jumping ahead of myself. Let's look at 16. I want to find the directional derivative at the point in the direction of V. So here's F. I need a point and a direction. Well, first off, the unit vector in the direction of v is going to be 1, 2, 3 divided by its length, which is square root of 14. Okay, and then I take the partials. With respect to x, y, and z are constants, so that's just going to be this. Evaluated at the point, y and z are both 1, so this is going to be a half. And for y, we have to use the quotient rule. We get minus x over y plus z squared. Evaluated at p0 is minus 4 over 4 is negative 1. And f of z, again, we use the quotient rule. Okay, it's the denominator times the root of the top, which is 0, because x is a constant, minus x times the derivative of the bottom, which is 1, over the denominator squared. So when we plug in the point here, we get negative 1 also. So the gradient is 1/2 negative 1, negative 1. The directional derivative at that point is the gradient dotted with the direction vector, and that's going to be half minus 2 minus 3 over the square root of 14, which is minus 9 over 2 square root of 14. And that's it. Let's look at number 22. At the point 0, 0, I want to find the gradient because I want to find the maximum rate of change at the point and the direction in which it occurs. So the direction is the gradient. So I find f of q, p is constant, f of p, I guess I could have done that first. So at 0, 0, this is going to be 1 plus 0 is 1. And at 0, 0, this is going to be 1. So the gradient at that point is 1, 1. So that is the direction of maximum rate of change. And the magnitude of that is the maximum rate of change. I'm just using the theorem. Okay, 30. I have this function, and I want to go from 80, 60 to 0, 0. So the vector that represents that is 0 minus 80. Remember, you go tail minus the head. I make that into a unit vector. Divide by its length, which is 100, and that's 0.8, negative 0.6. Okay, now the partial with respect to f here is 0.04x with respect to x. With respect to y, it's negative 0.003y squared. So the directional derivative at the point 80, 60 is, okay, at that point, this is going to be 3.2, and at the point, this is going to be negative 10.8. So it's the gradient dotted with the unit vector is 3.92. Now what does that mean? That is the rate of change of the depth at the point 80, 60 in the direction of the buoy at 0, 0. The rate of change is increasing since it's positive at 3.92. What are the units here? Meters per unit of time. So the depth's increasing as you go towards the buoy. That was a pretty interesting problem, I think. Okay, let's do 40. At the point negative 1, 1, 0. Here I want the equation of the tangent plane. So f, the function, we get everything on one side, so we have it equal to 0. And we want it in the direction of 1, negative 2, 0. So f of x is 1, f of y, negative 2y, f of z is negative 2z. At the point, this is 1. At the point, it's negative 2, and at the point, it's 0. So that's how I get this direction. So I have 1 x plus 1 minus 2 y minus 1 plus 0 z minus 0 equals 0. That's the equation of the tangent plane. So that's one thing. Then I want the equation of the normal line. Now the symmetric equations are this. Okay, and for 46, I'm going to go to Maple. Okay, so let me open it. Let's see, classic. Okay, for 46, what I want to do is I want to use computer to graph the surface of the tangent plane and the normal line on the same screen and choose the domain carefully. So what I want to do first is I always do restart as my first command. I want to use two packages. I want to use plots and I want to use vector calculus package. And I'll show you what's in that. When you use a colon, it suppresses the output. When you use a semicolon, you can see what commands you use. Now I want to use the gradient here. I'm going to come back later and do that. But the first thing I want to do is let me define J as a plot. I'm just going to call it J. You can call it anything you want. But implicit 3D plot, I'm going to plot it. And my f is x times y times z equals 6, because the level, let's see, yeah, that's my equation that I want to use. And the plane, when I worked this out, was, I guess I'll go back and do that. Let me go back and do that. To show you this, but you should already know how to do this. That's my f. And the point is 1, 2, 3. And f with respect to x is yz. F with respect to y is xz. And f with respect to z is xy. And evaluated at the point 6. Evaluated at the point, that's 3. Evaluated at the point, that's 2. So the equation of the tangent plane is 6 x minus 1 plus 3y minus 2 plus 2 z minus 3 equals 0, or you get 6x plus 3y plus 2z equal 18. Now that's what I'm going to sketch in Maple, so let me bring that back up. So here, I'm going to also do the tangent plane, 6 times x plus 3 times y plus 2 times z equal 18. So I'm going to sketch those on the same axis. And I'm going to go from, again, this text practice, you just pick a good domain and range. Okay. No, I wanted to, actually, let's go back. Let me go back and suppress that. Okay, because I just defined that. I'm going to graph it later. Let me define that as a space curve. And this is the tangent line. So let me go back in the notes and show you how, or the normal line. The equation of the normal line, remember, is the point. Let me do the parametric equations plus the direction. The direction is the gradient. So this is del f at the point is 6, 3, 2. So this is the direction I want, and the point is 1, 2, 3. So that's how I get the equations for the normal line. So in Maple, oops, I'm going to plot that as a space curve. Don't forget your times. Okay, and this took a while to get, but I picked negative 0.1 to 1. And again, I'm going to suppress it because now I'm going to display them both together. J and S. So I got the normal line, the tangent line, and the surface all together. So if I'm going to spin this around, I think the best way to see is right there. And I can right click to get my axes boxed. And as I turn it around, oops, you can see the tangent plane in the surface, let me, right there, and the normal lines coming out perpendicular at that point. So let me try to get the, see if it's easier to see if there's no color on it. Let's just go back to the regular color. So there's a good picture. You can see the tangent plane. The tangent plane's flat, there's a surface, and then the normal line coming out of it. All right, now the vector calculus package, let me define G to be the gradient. The gradient is a command, and you just give it the function x, this is just a little extra on the side, c minus 6, that's capital Fxy equals 6, and then you tell it that you have what variables you have. So we have x, y, z, you want it with respect to x, y, and z, and you get this. Now, the e's, the ex, ey, ez are the I, j, and k. So Maple uses ex, ey, ez for I, j, and k. So this is what we got for the gradient vector. If we want to plug in our point, we just eval g, that's why I defined it as g, at x equal 1. Our point was 1, 2, 3. And we get 6, 3, 2. So that's what you get when we worked it out by hand. So Maple will do that for us. Okay, so this was number 46. All right, let's move on and look at 48. 48, we want to find the gradient vector and use it to find the tangent line to the level surface. So g is x minus y squared. The gradient of g at the point 3, negative 1 is 1, negative 2y. That's gx, gy at 3, negative 1 is 1, 2. So when the level surface equals 2, we have x minus y squared equal 2. All right, then we have the equation of the tangent plane, actually tangent line, since we're only in 2 dimensions, is 1x minus 3 plus 2y plus 1 equals 0. We get x plus 2y minus 1 equals 0. Now let me okay. Now the graph of this, okay, we don't need Maple for this, is a parabola. This is x equal 2 plus y squared, sideways parabola. And at the point 3, negative 1, the gradient, g, is 1 in the direction of 1, 2. So that's del g at the point. And the equation of this tangent line is x plus 2y minus 1 equals 0. Okay, so there we go. Hope this helps on some of your homework problems.